Welcome to The Explainer. Today, we're pulling back the curtain on the invisible magic that powers your radio. We're going to break down exactly how a signal gets from the station to your speaker using one of the most fundamental ideas in all of communication: amplitude modulation.
I mean, have you ever really stopped to think about that? It seems so simple. You just turn a dial and boom, there's music. But the answer is this incredible story of physics, clever engineering, and some really tough problem solving. How do you actually send something like sound across miles and miles of empty space?
Because here's the secret. Sending a raw audio signal, like your voice or a piece of music, is basically impossible over any real distance. It's just too weak. But figuring out how to get around that one huge obstacle, well, that unlocked the entire modern age of communication. Okay, let's dive right in.
So before we can even get to the really cool solution, we have to truly understand the problem. And put simply, an audio signal all by itself just doesn't have the juice or the right physical properties to travel very far through the air. It just fizzles out.
It's the most logical first thought, isn't it? If the signal's too weak, just build a massive antenna, crank up the power, and blast it out there. Makes sense. But the laws of physics have a very, very surprising answer to that idea.
Yeah. You heard that right. To efficiently broadcast a typical audio signal, you would need an antenna that is roughly 15 kilometers tall. That is almost twice the height of Mount Everest. It's not just impractical, it is absolutely, wildly impossible.
So, here's the big takeaway. We couldn't just throw more metal at the problem. The issue wasn't the hardware, it was the signal itself. We had to find a clever way to package our audio information onto a different kind of signal, one that was actually built for long-distance travel.
And this is where the genius solution comes into play: the carrier wave. Instead of trying to scream that weak little audio signal into the void, engineers decided to send a really powerful high-frequency signal, the carrier, and then have the audio just hitch a ride on top of it.
That hitching a ride process? Well, that's called modulation, and it's the name of the entire game. The best way to think about it is like this. Your message is a letter. You can't just throw that letter across the city, right? But you can attach it to a powerful, high-speed drone. That's our carrier wave. The drone is what actually makes the long journey, but the letter inside is what holds the information you actually care about.
And this is the secret to AM radio. The carrier wave is just a simple, consistent, high-frequency wave, totally boring on its own. But when we apply our audio signal to it, the carrier's amplitude, that is, the height of its peaks and valleys, gets reshaped to perfectly trace the original sound. The information is now literally encoded in the shape of this powerful new signal.
Now, this was a revolutionary idea. It totally worked. But, and there's always a but in engineering, this first version of AM, while it worked, was incredibly wasteful. It was like using a sledgehammer to crack a nut.
Okay, so here's a crucial detail. The modulated signal you create actually has three separate parts. Right in the middle is that powerful carrier wave we talked about. But the actual message, the song you want to hear, gets duplicated into two sidebands on either side of it. So the carrier is just the delivery truck, while the sidebands are holding the actual cargo. And this chart just lays the problem out perfectly. A staggering 2/3 of all the energy used to transmit a standard AM signal is spent on the carrier wave alone. That is pure power being wasted sending a component that contains zero new information. Only about 1/3 of the power is actually used for the parts that are carrying your song. So this massive inefficiency got engineers asking a very simple but brilliant question. Can we trim the fat? Could they figure out smarter ways to send only the parts of the signal that actually matter?
And what happened next is just a masterclass in efficiency. First, with DSB-SC, they just chopped out the wasteful carrier wave. Boom, an instant 66% power saving. Then, they realized the two sidebands were identical copies. Why send both? So with SSB, they got rid of one of them. That saved even more power and cut the signal's footprint in half. And VSB is this clever hybrid, mostly for TV signals, where you keep one full sideband and just a little vestige of the other, just to make sure you preserve all the crucial details in the picture.
This table sums it all up beautifully. We went from a simple but really inefficient method to these increasingly clever techniques that saved enormous amounts of power and precious bandwidth, which is basically how much room a signal takes up on the airwaves. As you can see, single sideband, or SSB, is the real champion of efficiency. It saves over 80% of the original power. That's just fantastic engineering. Okay, so we've mastered sending the signal as efficiently as we can, but that's only half the journey. A receiver, like the radio in your car, has to perform an equally impressive trick. It has to pluck that one specific signal out of a sky that's just full of noise.
I mean, just think about it. Your radio is being bombarded by signals from countless stations all at the same time. It needs the sensitivity to hear a very faint signal from far away. It needs the selectivity to lock onto just one station while completely ignoring all the others right next to it. And finally, it needs the fidelity to perfectly rebuild the original sound so the music sounds just right. That little box is doing a remarkable amount of work.
This entire story, from an impossible 15-kilometer antenna to a hyper-efficient signal that uses a fraction of the power, it's really a story about human ingenuity. The big thing to take away from this is that the core challenge never really changes. How do we send more information more efficiently over greater distances? We solved it for analog radio, so the question now is, what's the next big impossible challenge